This video covers gravity. Now you've seen this equation before. This is a force of gravity is equal to capital G, which is our gravitational constant, 6.67 times 10 to the negative 11, times m1 times m2 over r squared, where r is the distance between the center of mass of the two objects. It's the distance between center of masses. Now this picture shows that normally when you're dealing with satellites or things orbiting, you will not necessarily be given the center of mass of the satellite, but you will be given the center of mass of the Earth. So you're just going to assume that the satellite is a point mass and everything else is going to work as is. Now here it's really important to understand that the force exerted on one is equal to the force exerted by the other. This F1 and these F2 are equal in magnitude but opposite in direction. Again, this follows Newton's third law. It's very common to see these types of questions on the multiple choice section of the AP exam to tell you what happens if one of the masses increases. What happens to the force on the other mass? Well, that increase is going to affect both of them equally. Now, if I ask you to solve for the gravitational force, or weight, you would tell me mg. Well, our own gravity, 9.8, comes from this equation, g, m1, m2 over r squared. So here you can see that one of the masses will cancel out. This is usually the mass of the object. And what's left is g m over r squared, where m is going to represent the mass of the planet, in this case Earth. Now this equation gives you the gravitational field strength at a certain point. Again, you can see this is very similar to our electric field strength, kq over r squared, where it's just dependent on a charge. Well, here we're dependent on that giant mass, in this case the Earth. Again, this equation tells you the gravitational field strength. On your AP sheet, you're actually going to be given this version of the equation, where you're going to have a negative sign included and an r hat. What this r hat means is this unit vector, which tells you the direction the force is going. Again, it's probably better for you to just use the equation we wrote earlier, g times m1 times m2 over r squared, to find the magnitude of it, and then find the direction through your own conceptual understanding. Again, we are going to be using this negative later because this negative means that it produces a bound orbit. And we'll see an example of simple harmonic motion where we needed that restoring force, but we'll see that a little bit later. In this example, it says how far from the Earth's surface must an astronaut in space be if she is to feel gravitational acceleration that is half what she would feel on Earth's surface. Now, you might think this is a straight plug and chug, but we need to remember that our gravitational field, or gravitational acceleration, is just g times the mass of the planet, in this case Earth, divided by r squared. Now r is the distance between the two center of masses. So when we are looking for the distance away from the Earth's surface, that means we have to include the radius of the Earth plus the distance that she is going to be away from the surface. Those two distances together make up the total distance. So this would be RE. And if she's over here, this would be the additional R. So in total, this would be the total distance between the center of mass of the two objects. Again, you want to solve for this little r. So that means we need to rearrange the whole thing. So we can bring little g down to the bottom, re plus r squared up to the top, square root, and then we want to solve for little r so we can subtract. So the distance that she needs to be away from the Earth's surface is the square root of g times capital M over little g minus re. If you plug in all of your numbers, again for capital G, we have 6.67 times 10 to the negative 11. For capital M, again, that's the mass of the Earth. These are going to be constants you're going to be given if you need to use them or actually calculate something. They're going to be found on your equation sheet. Little g, again, we want to know when she would feel half of what she would feel on Earth. So if on Earth it's 9.8, we would want her to experience 4.9. And then again, the radius of the Earth is 6.37. All of this information can be found from your equation sheet. If you put all that into your calculator, you should get 2.64 times 10 to the 6th meters. This is the distance away from the Earth's surface, not total distance away, but the distance away from the Earth's surface she needs to be in order to feel half of the gravitational acceleration she would feel on Earth. So let's look at this equation again. We know that as r decreases, our force of gravity is going to increase. But let's say that you dig a hole through the center of the Earth. Now, this is actually a very common AP problem. So when you jump down and are at a radius r from the center, the portion of the Earth that lies outside a sphere of radius r does not produce a net gravitational force on you. That means that the portion that lies inside of the sphere does. This implies that as you fall, the sphere changes in volume, mass, and density due to different types of rocks. This also tells us that your weight, again your force of gravity, actually decreases as you approach the center of Earth from within the inside of the sphere, and that it behaves like Hooke's law. You will oscillate. Again, the density of the planet depends on the mass over volume. So in this case, the volume of a sphere will be 4/3 pi r cubed. So if we're trying to determine how much of the mass is actually depending how much force of gravity we experience, then we can say that our density times 4/3 pi r cubed, equals the mass that's affecting us. So as r starts to decrease, so will the mass that affects us. So let's use that information and plug it into our force of gravity equation. I'm going to use capital M for the mass of the planet, little m for the mass of the person, or the object. Again, capital M is going to be replaced with rho, 4/3 pi r cubed. And this simplifies down to g times rho, 4/3 pi m times r. Now, all of this inside of parentheses are going to be constant. The only thing that's actually changing is this r. So we can replace this entire thing inside the parentheses with a k to represent a constant. Again, we can see how this relationship is very similar to Hooke's law. Remember that in simple harmonic motion, we saw that this particular equation created simple harmonic motion, meaning that you are going to oscillate. Again, going back to the fact that you will oscillate as you go through the center of the Earth. So let's try this example. It says a 150 kilogram astronaut now stands at the bottom of a hole that is 1.6 times 10 to the 6th meters deep. The radius of the planet is 3 times 10 to the 6th meters. Assume that the planet's density is uniform and our rho is equal to 7 grams per centimeters cubed. We're asked to find the force of gravity on the astronaut. Again, as you go to the center of the Earth, the force of gravity, or the mass that affects your force of gravity, is going to start to decrease. Again, it's going to depend on the density of the Earth, which is the mass divided by its volume. So to determine the mass that affects your force of gravity, it would be density times volume, or density times 4/3 pi r cubed. Again, we can plug that in for the mass of the planet. That'll be rho, 4/3 pi r cubed. Same derivation. Again, being able to go through the entire process is going to be important. Times the mass of the astronaut over r squared. the distance from the center of mass to where the astronaut will be. Again, these r's will cancel out, and you're left with one r on top. And you're left with g times rho, 4/3, pi, r, m. Now, the last thing you need to do before plugging in your numbers is solving for rho. We're given rho, but it's in grams per centimeters cubed, and we know that we have to work in kilograms and meters. So if we have 7 grams per centimeter cubed, we can convert that to 1,000 grams per kilogram. And because the centimeters cubed is cubed, we need to do 100 centimeters per meter 3 times. So that our rho is now 7,000 kilograms per meters cubed. So now we can plug in all of our numbers. Again, g is 6.67 times 10 to the negative 11. Rho is now 7,000. 4/3 pi. The distance from where the center of mass is to where we are is 1.6 times 10 to the 6th. And then the mass of the astronaut was 150 kilograms. 469.4 newtons is our force of gravity acting on the astronaut. In this example, a hole is dug all the way to the other side of the planet. The astronaut jumps in the hole, and we're asked to describe the astronaut's motion. Again, we said based on the equation that we're going to have simple harmonic motion, and we're going to oscillate about the center. Here we're asked to find the force of gravity on the astronaut at any position r, and the time it takes to complete one oscillation. Again, this is a force of gravity equation that we just derived. Remember that force of gravity is equal to mass times acceleration. In this case, we can write acceleration to be the derivative of position with respect to time. Second derivative of position with respect to time. Again, this is a review of the simple harmonic equations that we derived earlier. So, we can replace r and the second derivative with a function that we know the solution to. Again, in previous examples, we've used x is equal to a cosine theta, or omega t. Here we can just replace it with r because r is just representing position anyway. We can make this substitution and say that this whole mess times a cosine omega t equals our second derivative of this equation. Again, I'm going to cancel out my m's here, so that could have gone out. And we're left with negative omega squared a cosine omega t. If you don't remember any of this, you should definitely go back and review the simple harmonic motion video. Again, a cosine cancels out with a cosine, and we're left with negative g 4/3 pi rho. Again, our mass is canceled out. Here, these negatives can cancel out, and we're left with, again, this is very similar to equations that we've seen before when we've derived our period. Remember that if I take the square root of both sides, omega is equal to 2 pi over t. Well, t is the period, the time it takes to complete one oscillation, and that's what we're trying to solve for. So t is equal to 2 pi. If a fraction goes down to the bottom, we can just multiply by the inverse. So this is 3 over g 4 pi times rho. This is the time it takes to complete one cycle. If you plug in all of your numbers, you should get a period of 4,492.9 seconds, which is about 75 minutes.